Today we're ready to start 802. We're going to start by talking about charge. What is charge? All matter is made up of charged particles, electrons and protons. And the electrons have negative charge, the protons have positive charge, so matter in this room under normal circumstances is neutral. It has equal numbers of pluses and minuses. We'll do more quantitative things later, but what are the units of charge? Well, the unit of charge is called the coulomb. And you can tell that the coulomb is a very big amount of charge. So we will often talk about the charge of a single electron, and that we will call minus E. The things I want to focus on today are not quantitative, but qualitative. Two very basic features of charge is that it's quantized and it's conserved. And I want to talk about each of those. So what does it mean that it's quantized? Well, it means that the charge of any object in the world is an integer. It's either minus E or plus E or minus 27E or plus 53E. And that's because it's made up of electrons and protons, and the charge of the proton is exactly the opposite as the charge of the electron. So one of them is minus E, that's the electron. One of them is plus E, that's the charge of the proton. So that is what we mean when we say that charge is quantized. Except for the fact that I actually just lied. If you get to look inside a proton, there are quarks inside with charges of either 1/3 E or minus 2/3 E. But those quarks are always bound up together inside of a proton. So long as you never actually try and take a proton apart and look at the quarks inside, what I said a second ago is true. This fact that I've just told you about charge being quantized, that's actually an experimental fact. There's no profoundly understood reason for it. We could imagine living in a world in which charge came in arbitrary fractions, even non-rational amounts. But the world we actually live in, charge is quantized in units of E. And this is something that experimental physicists regularly test. They regularly do experiments with greater and greater and greater precision, looking to really check, is the charge of the electron minus 1.00000 times the charge of the proton, or maybe it's 1.0001. That's regularly tested, and to the best of anyone's ability to do any experiment, it has always turned out to be that the charge of the electron is exactly minus the charge of the proton. Now, what about charge being conserved? That's fundamental also, and we're going to be doing some experiments ourselves to see what that means. What does charge is conserved? What do those words mean? It means that I can't make charge out of nowhere. If I want to make it charge an object up, the way I do that is by separating positive and negative charges. So this is a plexiglass rod. It's right now neutral. I'm going to make it positively charged, and I do that by ripping some electrons off of it, getting them onto this fake fur. So I claim that now, after rubbing the rod like this rod is positively charged, and this fur is negatively charged. But the total charge of the two together is the same as it was before, which is 0. So the conservation of charge means that I can move charge around, I can take some negative charge off the rod and get it onto the fur, but I can't create net charge out of nothing. Okay, so how am I going to convince you that this object is now charged? Well, I'm going to do that by bringing it near the tinsel. You see the tinsel reacting to the presence of the rod. In fact, I'm going to transfer some charge from the rod onto the tinsel. And if you look at the tinsel now, you will see that the different strands of tinsel are being pushed away from each other. That's because all those strands of tinsel now are themselves charged. And the third basic fact about charge that we're going to see today is that like charges repel and opposite charges attract. So all of those bits of tinsel have the same charge, by convention called positive, and they're repelling each other. And if what I'm telling you is true, this is positive, the tinsel is positive, and the rod should repel the tinsel. And you see that as I bring the rod close and push, and you can see that my positive rod is pushing the positive tinsel away. That tells you that the rod and the tinsel have the same charge, and this is by convention the charge that we call positive. Now, if charge is conserved, there has to be negative charge somewhere, and it has to be on the fur. So let's see what happens if I bring the fur close to the tinsel, and you see that the fur is attracting the tinsel. So one last thing I want to do is I want to show you what happens when I bring a charged rod right next to a neutral balloon. And let's see whether we can see the charged rod attracting the balloon. Look at that. Now, that balloon was neutral. How do I convince you it's neutral? Well, I'm going to ground the balloon just so you believe me that it's neutral. That's a neutral balloon. And I'm charging this rod positive. And I bring the rod close, and the rod is very definitely attracting the balloon. I can pull the balloon all the way over here with my positively charged rod, and yet the balloon is neutral. So how is that working? The key thing is that the balloon is a conductor. So when I bring the positive rod next to the balloon, what's happening inside the balloon is that charge is being separated within the balloon. And we get a little extra negative on this side, a little extra positive on that side, because the positive rod is sucking negative charge this way, inside the balloon. And as soon as that happens, then I have the negative side of the balloon close to the positive rod, and so the positive rod is now attracting the negative side of the balloon. So my balloon is at this moment neutral in total, but it has a negative side and a positive side, and the positive rod is attracting the negative side of the balloon, and that's what's going on here. So these are very simple demonstrations, but they show you that opposite charges attract, same charges repel, and that the way you charge an object up always involves separating charge because charge itself is conserved. So, last time we learned how to charge an object up. We learned how to take an object and give it a net electric charge. Once we have charged objects to play with, what we discover is that they feel forces. If I have two objects here and they have the same charge, either both positive or both negative, they repel each other. They push each other apart. On the other hand, if I have two objects here and one of them is positively charged and one of them is negatively charged, they feel a force, and the force attracts them towards each other. So, doing this concretely on the board, if over here I have a positively charged object with a charge that I'm going to call Q1, positive as I said, so we are always going to use the letter Q for the charge of an object. And then suppose that up here I have a second object, which is also positively charged, but maybe it has a different positive charge, so I'll call its charge Q2, also positive. Then in a situation like this, I have two positively charged objects. They feel a force, and the force on these objects does not point in any random direction. This object doesn't feel a force pointing off this way or some crazy direction. The force is central. A central force is a force that points along the direction of joining the two objects. So this object feels a force in this particular direction, shown here, and we're going to call this force F12. And this object, again, feels a force not in some crazy random direction, but in this direction, and we will call this force F21. So a word about this notation. When I write F12, what do I mean? I mean the force on object 2, this second digit here tells me that this force, shown by this vector, is the force on object 2 caused by the interaction between the two objects 1 and 2. So it's the force on this charged object caused by the interaction between these two objects. These two objects are positive. They feel a force that is repulsive, and the force on this one, object 2, is this direction and is F12. Similarly, F21, that's the force on object 1 because of the interaction between 2 and 1. So it is a vector pointing in this direction. Now, in the other possible case, let's suppose that I have a positive object here with a charge Q1, positive. But this time, let's suppose that the other object, which, I don't know, I'll put it right there, it has a charge Q2, but this time, this Q2 is negative. So in this case, once again, the force is central. The forces on both these objects point along this line, joining the two of them, but this time, the forces point this way. This force, again, is the force on 2 caused by the interaction between 1 and 2. And this force, again, is the force on 1 caused by the interaction between 2 and 1. But this time, the forces point towards each other. the positive and the negative objects are attracted to one another. What we're going to see is that the electric force, shown by these white vectors, is, when written as an equation, very similar to the gravitational force between two objects. What you learned in mechanics was if I had two objects with mass m1 and m2, there was a force of gravity between them. But the central difference between electric forces and gravitational forces is that in gravity, the vectors always point out like this. Gravity always sucks. Gravitational forces can only ever be attractive. Whereas in electromagnetism, electric forces, they can be attractive like here, but they can also be repulsive like here. This possibility does not exist on the gravitational side. So if I want to write, for example, F12 as an equation, how do I do that? Well, the first important fact about F12 is how to write its direction. And the way I'm going to write its direction is I'm going to define a unit vector, which I will show right here. I'm going to define a unit vector, which I will call r hat. And r hat, and in fact, I'll call it r hat 1, 2. R hat 1, 2 is the unit vector that points. It's a unit vector pointing from 1 in the direction of 2. And F12 is in the direction r hat 1, 2. And from experiment, we learn that the electric force between two objects is proportional to both their charges. So it has a strength that is written as Q1 times Q2. And what you see from this is that right away we get the basic feature that like charges repel and opposite charges attract. We get that just from what I've written so far. The equation isn't done yet, but you already have, if Q1 times Q2 is positive, then F12 points in the direction of R12, which is this case. If Q1 times Q2 is negative, which means if they have opposite charges like here, Q1 times Q2 is negative, then F12 points in the minus R12 direction, which is what I've shown there. This F12 is pointing in the minus R hat 12 direction. We get that just from this. And then, just as in gravity, the strength of the electric force falls off like 1 over the distance between the two charges squared, where this distance r is the distance between these two objects. So the farther apart they are, the weaker the force, and the force falls off like 1 over r squared. And then the last thing is we need a fundamental constant of nature. For gravity, the fundamental constant that went here was called Newton's constant. There is a different fundamental constant of nature that goes here, which we are going to refer to as K. And this equation, which describes the force between two charged objects, is a fundamental law of nature based not on earlier principles, but based on things we have observed about how charged how charged objects behave. It's based on measurements and observations of nature, and it's referred to as Coulomb's law, named after a French scientist from the late 1700s, who was the first person to articulate this fundamental law of nature as we now understand it.